it's a great pleasure to introduce Ernesto Lupercio, who will speak on Hodge numbers in quantum toric geometry. And let me just say, so Ernesto always had fantastic new things to tell us about. And I think it's also true that Ernesto has played an important role in the development of the Institute here at through a number of visits and opportunities.
Thank you so much. Thank you so much. Can you hear me better? Well, it's a great honor to be here, especially because it is to celebrate 50 years of mathematics of Verjovsky teaching. Of course, we all encounter early on a paper by night that kind of marked our career. And depending on the generation we belong to, these papers were various. In my case, being so close early on to Rockon and Graham Siegel, of course, many of these papers appear on my path. But Bernardo and I, very early on in our careers, read these wonderful. If you try to understand what is a geometry, it will be very confusing. When you read these explanations by Nigel, remember, Nigel asked us to do what we wanted to do instantaneously, you know. Because Nigel had that enormous talent of making everything seem very easy. And this is the quality of lucidity. You must take away all the complications and get at the essence of the things. So thank you, Nigel, for so many mathematics. Also, I'm very honored because, of course, the mission of the Institute of Mathematical Science of America is to highlight that America can make you interact according to the world. And Nigel has also been a key player by having so many extraordinary Latin American mathematicians, nurturing them, and then making the mathematics of Latin America richer, more interesting. And today I have one too many slides, but even though you may see things, there are just an impressionistic survey of what is going on here, how Hodge numbers are a landing post that allows to start exploring one of our methodologies in first Kjell, Sally, and Ludwig, which is very here. So I'll just give us a little bit of a survey, kind of really high above the trees. So you'll see a lot of letters flying around in the slides. Ignore them mostly. And I will say just in prose what is going on. It's kind of a survey of the subject. And the subject is that subject of quantum toric geometry. So in classical toric geometry, well, you have torque. You have typically, you are thinking of the moment map picture of integral systems. Well, when you have these complex stories, you can think of that you are equivariantly compactifying with the associated manifold value ways depending on information. This information coded typically in the moment polyton, combinatorics and geometry of moment polytons. And so when the complex torus is important, toric geometry, obviously. In toric geometry, you have both these complex torus and also the real tori that are the images of points in the moment map picture of the Kähler toric variety. Imaginary is projective. Well, I cannot point because the laser is not working, but if you have this moment map, typically genetically the intersection of points are real torus. And again, tori are very important in this project, of course. So what I'm going to do to produce quantum toric geometry? Well, there is a while the torus is quite in terms of DC star, C star, C star, star, and classes of characters and characters. And it's a thing that you start with the theory from that. What we're going to do is we're going to change the term for quantum toric or non-commutative toric. Quantum toric are medium, but they don't, if I prefer the phrase quantum toric that are non-commutative torics. A little bit less confusing. They are non-commutative spaces, but they are the analog of abelian groups in this category of non-commutative spaces. So I'm going to change all the toric for quantum toric. So quantum toric geometry can be thought of as a deformation with a deformation parameter h bar. And while in low dimensions h bar is a number, in quantum toric geometry h bar is a collection of numbers. So we will have a deformation parameter h bar on the whole field of toric geometry. And many results from the classical theory have their immediate counterparts in quantum toric geometry. And some of them, their proofs are not entirely obvious, but they remain true. And a lot of it remains true, not everything remains true. There's a very good generalization of toric geometry. We find the usual suspects, fans, lattices, right? So now there are quantum fans and quantum lattices, and I have to tell you what is a quantum fan and what is a quantum lattice, and all these stories. So the basic block is the quantum dots. And this space kind of acquired personality in the famous paper of Alan Cohn in 1985, non-commutative differential geometry. But he studied this space carefully from this geometric point of view for the first time. Well, what is it? The quantum torus, if you think of just provisionally, naive, as non-commutative spaces, as non-commutative algebras, the opposite category to non-commutative algebras, just as you could think of affine schemes as commutative rings or as just or it can be called as determined by its algebra functions. So you can think that these non-commutative spaces is neither the first order of approximation and non-commutative algebras. And then this is the non-commutative algebra that corresponds to the quantum torus. It has these two generators, x, y, and it's non-commutative, but not vastly non-commutative. It's slightly non-commutative. X, y, y, x times e to the 2 pi I h bar. And today, h bar is going to be a real parameter, not a computer. So today, h bar is going to be a real parameter. This is really von Heisenberg-Jordan commutation relation from the 1926, 1925, and 1926 papers, as written in 1927 by Hermann Weyl in exponential form. So you have this, and this can be realized, of course, as an algebra of operators in quantum mechanics. Now, there's this important arithmetic dichotomy that is for this parameter h bar in the definition of this algebra. In fact, for using non-commutative geometry, the natural morphisms are not algebra morphisms, but rather bimodulus. And then you realize that different algebras really are meant to be the same in non-commutative space. These are the so-called monetary equivalent algebras. They are really meant to be the same in non-commutative space. You are meant to identify algebras with equivalence. And the arithmetic dichotomy appears for this reason. When h bar is rational, even though the algebra, so much h bar is not zero, is really non-commutative, it is secretly commutative when h bar is rational, because it will be monetary equivalent to the algebra h bar equals to 0 to the commutative algebra, if and only h bar is rational. So you have this arithmetic dichotomy where the space is truly non-commutative only when h bar is irrational. And you want to form a modular space of these algebras, Well, it's Jones value, you see, because rational values. You cannot formalize, and we want to formalize non-commutative. This is really one of our objectives. Okay. So Alarcon pointed out a beautiful geometric interpretation for this non-commutative value. So it said, well, this non-commutative algebra is really the algebra of functions in a space. What space? The space of leaves of the canonical foliation of slope h bar. So you take the canonical foliation of the slope h bar. That is to say, you take all the parallel lines in R2 of that slope, and then you divide by the lattice set 2, and then you get the Euclidean space, and you project, and you get the foliation. And Kohn pointed out that this algebra is meant to be the non-commutative algebra functions on this space of leaves that typically, as soon as h bar is irrational, becomes non-causal, because every leaf is everywhere. So what does it mean? Well, this is a little bit canonical foliation. Of course, it's really important to look at its hologram. So that is to say, if I take a transversal circle and tell you what once, I will come back with an angle, and then the hologram of the canonical foliation, as the case in the picture. So what it means is that you form a groupoid, a holonomic groupoid of the foliation, and then you take the convolution algebra of the groupoid, and this is the algebra that you're meant to associate the space of leaves of foliations. And when you do it for this foliation, modulo Fourier transform that gives you a monotonic group, you get the algebra that I mentioned before, this algebra for the quantum torus. So the algebra for the quantum torus can be obtained as the convolution algebra of the groupoid associated to the foliation, the holonomic groupoid of the foliation. And that's how you get the algebra from the foliation. And of course, now it's very easy to see that if h bar is rational, this foliation is very different than if h bar is not rational. And also that there is an SL2Z action on the h bars that will leave the theory invariant. In any case, you have non-commutative algebras. These are non-commutative spaces when you identify the equivalents. Then you get these groupoids, you get these stacks. When you identify something that is called Morita equivalents as well. Although it's likely different characters, equivalents of categories. The stack is a category, and the equivalence of category gives you a group. The equivalence of category, equivalence of category gives you a stack. And then you get the convolution counter from stacks to non-commutative space. Now, so we have here 4 avatars for the quantum torus. The algebra is AH. The Morita equivalence class of the algebra is T2RH, that kind of T. Then there's this other kind of T that represents the stack, that's a highly non-separated stack. And then you have the action, the reals on the torus. You have these 4 characters for the quantum torus. I'm going to call this one the quantum torus. I'm going to call this one the non-commutative torus. And I'm going to work most of the time with the quantum torus, and only at the end apply, if necessary, the convolution function. So I'm going to be working with really the foliations rather than the algebras, if you want to think about it that way. And so there is avatar for the quantum torus. So, but of course, equivalence of categories that I mentioned, geometrically in this case, could be construed as the ability of, rather than thinking of the whole holonomic groupoid of the torus by that foliation, just think of the rotation group, the holonomic, acting on the transversal, on the circle. So it is the same to have the circle acted on by the rotation as it is the torus acted on by the real line. It is the same category, and even geometrically so. And you get the same answer. In fact, if you do the convolution algebra of that groupoid that is the circle acted on by a discrete group, isomorphic to the integers, then you get the algebra for the non-commutative torus. That's okay, one will fully transform. But of course, then you have S1 acted on by the rotation rather than the torus acted on by the real line. And you can get the universal cover of this one as R, and then you have R acted on by the subgroup of R that is generated by 1 and H bar. And this subgroup of R generated by 1 and H bar, I would call a quantum lattice. So if R belongs to a quantum lattice, the quantum torus. That's all I am saying. But of course, the geometric image of this quantum lattice, if anybody says for order 2, is this dense dust inside of R. It's a rank 2 abelian group inside of R. It's okay, but it's not a lattice. It's a quantum lattice. This lattice also appear in the theory of quasi-crystals, and they are called quasi-lattices in the theory of quasi-crystals. But in the theory of quantum lattices, I have called it quantum lattice. It's cute. It's okay. So I call it a quantum lattice. So I get quantum lattice, and dividing this R by this quantum lattice, I get this quantum torus. The dimension seems a little bit off if you think about it. The two-dimensional quantum torus, I divided R by the lattice, and I'm getting a two-dimensional quantum torus. Well, I can generalize to CD and a finite free abelian group, finitely generated free abelian group, subgroup of CD, gamma, called a quantum lattice. In fact, I will require today that is inside R gamma. And then I add CD by gamma, and this is a quantum torus in arbitrary dimension. It is a stack, it's a non-separated stack. And now I have the advantage of while in the past, in problems starting on that, you have spectral triple or that kind of thing, it was kind of the information to have a non-commutative smooth manifold. Now I have the information to have a non-commutative K element. So now I can think of it as a non-commutative K element.
Is there any restriction on the rank of the lattice?
Yeah. Of course, you want this lattice to be right at least the dimension of the space and more.
It could be 27
Yeah. And that's all. And you'll see that produces an incredibly nice picture. You'll see them. In any case, quantum torus is something called a Picard style, whatever that is. You like that kind of thing. And they form a quantum torus form a category. There is a subcategory, the category of Picard stacks, as defined by Arthur and Lupercio, etc. So, but in real life, when you are thinking about toric, in the books of toric geometry, there is this lemon in the book that says, oh, well, a map of toric is really a map of lattices. You have this kind of lemon in the books of toric geometry. And you have this kind of lemon here, so that you don't have to think about Picard stacks and that kind of thing. The category of quantum toric stacks and blah, 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 is equivalent to the category of quantum lattices, and then with morphisms of the quantum lattices that are extremely natural linear objects that you can define, that are just measures. So the category of quantum lattices, and this is a theorem, you have to prove this, but you prove it, you go through all the values, and it's true. So it's the same lemma as it is for classical toric geometry, for this quantum toric geometry. The answer quantum lattices, not lattices. So when I think of quantum P1, P1 was C star, and you have 0, and then you have infinity. And in quantum P1, what you have is you have a quantum torus, and now you have 0 and you have infinity. And then you move 0 and infinity to a quantum torus, and you get quantum P1. So this is an example of how you could produce by chance one of these quantum P1s. Fixing gamma, and imagine that gamma is 1 divided by 1 and square root of 2. But it could have many more rationalities and transcendentality there. And the number theory is important. But imagine that is just 1 and square root of 2. Then you could glue that way these two non-commutative charts that are partly compactified non-commutative toric by adding just the 0 and the plus infinity. And then you glue them. You get this non-commutative, this stack, this highly non-separated stack, that is quantum P1. And you have the free non gamma. You can move gamma, and get many quantum P1. If gamma is rational, generated by rational numbers, if you have a rational lattice inside of R, you recover weighted P1s. You recover all of them. It's not entirely trivial the fact that you recover all of them, but you recover all of them, and how they are located. But now you can see that gamma is given by 1 and each bar. And each bar is the coordinate of the modular space of quantum P1s. Well, this is what we want to organize in a modular setting. There is this problem in dimension counting where quantum P1 it has a two-dimensional torus inside there, you know. But there is this interesting fact that just even P1, if you think of it as C star together with a gel, talking about these years. Now, well, like C star cross B, Z, that is of the homotopy type of S1 crosses 1. And then even our ordinary P1 has a two-dimensional homotopical torus in the middle of these 2 points. And that's what we're going to do. We're going to turn on the gel to solve this problem of the modular space, to solve this problem of making an animal mistake, we turn on the gel. And in fact, having more of these irrationalities there is like having marked points in the structure. I'll explain everything. In any case, this is about turning on the gel. But this is an important example, P1, so let me talk about it briefly. P1 is a model probably, of course. So P1, typically P1 has the Hodge surface and an elliptic vibration that makes it, you can think of P1 as the portion of the Hodge surface by this elliptic vibration, by this. And you can think of this elliptic vibration as a foliation, a holomorphic foliation. So, well, what is going on in the following? And this is the picture that we need to understand. And it's the fact that we have P1, we have the top surface, we have this elliptic vibration, and to make it into a quantum P1, what you do is you move a little bit holomorphically, this holomorphic foliation, you still get something topologically at top surface, but as you move this, you get this foliation, and if this H bar is irrational, this foliation gets, if you take exactly the 2 points here, you get exactly a clonical foliation inside the topological top surface, and you can get a new complex. As you move the parameter, you are very complex structure on the space H. Let me just call it perhaps, just to avoid confusion, S3 crosses 1. So you have a complex structure, but then as you move H bar, you start moving the complex structure of S3 crosses 1, and you get all these holomorphic foliations. And now I'm near the disaster here. You move all these holomorphic foliations, and that's the picture that I want to give you to keep in mind. What we're going to do for toric variety, we're going to put a toric variety here, and we're going to the bottom if you prefer. And then here we're going to place a space N, and here there is an abelian variety. So you have an abelian variety, but as you move it, then you get this topological manifold, but then you get some vector space here, making these chronicle foliations are all strata of the stratification of the moment map. The moment map still exists. The moment map still exists. And as you move in the stratification, you exactly have all these chronicle foliations that you are doing by the information of a fan. And that's the picture that you have. And of course, you are getting now this complicated foliated space, and this is the non-commutative version of a toric variety. But now we can only that's the whole point. So that is the story for P1. And the general story with manifold N, in the general story, this manifold N is called an LVM manifold, and it exists for any toric variety And then as you deform, you get all these complex structures on these manifolds. And you could even pass walls and change the topology and organize all toric varieties in a module space. So, another example here, another possible example is the Calabi-Eggman manifolds. Now you have here products of other two spheres rather than just S3 process 1. You could have for friends like S7 process 1, or we could have, well, anyway, we could have all these other products of spheres here, and here it will be a product of perimeter spaces, still a toric variety. And then you will have the same story, and these are the Calabi-Eggman manifolds. You get these complex structures. Typically, this is a factory. As you move along the toric varieties, this is a factory of compact, non-scalar manifolds. All these manifolds are a compact complex manifolds, but they are clearly non-scalar. So you have now this factory, enormous factory of, and this is due to Lopez and Verjovsky and Meersseman. And this is this picture. This is from 2004. Almost the principal models of the projected toric variety in the commutative case. And the generalization is our non-commutative generalization where we let the base space to be a quantum toric variety, a non-commutative space as H bar. So if you form a modular space with the H bars, if you form a modular space with the H bars, the coordinate H bar, these are the possible H bars, the modular space of toric varieties, the rational points are the classical toric varieties, and the irrational points are the quantum toric varieties, the ones that are non-commutative spaces. So you have exactly this picture. Anyway, in these worlds, you can think of it as toric geometry or monomials of what kind. Well, here the purpose of this slide was to show that now it's these monomials where the exponents could be rational numbers in the theory of monomials for these toric varieties. And so what you have, traditionally you had the moment map was rational polygons. But now it's possibly irrational polygons. So you now get all possible funds, irrational funds included. If your fund is rational, then you have a classical toric variety. But if your fund is irrational, then you get a non-commutative space that's a quantum toric variety that is an equivalent rectification of a quantum torus. So exactly irrationality. This is what there are quantum lattices, and now quantum lattice correspond to quantum tori, I already said it. And this is what a quantum fan looks like. You have a quantum lattice, and now you have a fan in the quantum lattice, and that's a quantum fan. But observe that it could be that you have just enough in rationalities to cover the rays. But it could be, as you said, that you have a whole bunch of more marked points in Rn to make the quantum lattice, generators of the quantum lattice. These are the extra things that you were asking for. So you are to imagine that there are marked points. So this is a quantum fan. Well, the correct notion is a calibrated quantum fan. So you have some Rn, N is bigger than B. It could be a million, it could be 3, it could be 2, and it could be a million. So to have enough generators, so enough irrationalities in the quantum lattice, when you remember how they come about, you remember H. So it's a map from the classical ZN lattice in Rn for N large to Rb. This H is a quantum lattice, but this H is what we call a calibration of a quantum lattice. So we calibrate the quantum lattice, and then we have the fan in the quantum lattice. And this is a calibrated quantum fan. And this is the correct object in zero. A calibrated quantum fan is the correct object in zero. It gives you a calibrated quantum toric variety that remembers each other and allows you to move H to form a modular space. So, well, this is the affine case. I mean, you can see the final star as a collision in the category from the fan to the category of G stars, blah, blah, blah. That kind of thing, but you can imagine, you just view with respect to the information defined. This is a little example with respect to P2. Now it's important. Nevertheless, you have this A, you have this calibrated quantum fan. And rather than using for us the moment map, we're going to use this version of geometric invariant theory, where what we do is we take the gain transform of the generators of the image of H of E1. V1, V2, Vn is H of E1, H of E2, H of En. So this V is the information, is a matrix for H. And we take the, well, we take this exact sequence and we take the A, we take the dual. This is called the gain transform to get this. With this A, you can write the dynamical system. You can write the group action on this complement of complements of the space. You know, the typical thing in toric geometry. But now the dynamical system is not that. It's not an action of toric. It's an action on a fine lattice. Of course, when A is rational, it becomes an action of toric. It becomes classical toric geometry. But when A is not rational, it is this action that is a bunch of chronic foliation actions depending on the strata. And then you can define by geometric invariant theory the quantum toric varieties, the calibrated quantum toric varieties. Well, you have the typical results in geometric invariant theory, and then you can show, for example, that quantum toric variety is a scalar star. Non-separated is nevertheless scalar star, if and only if delta is a polytopic alpha. That kind of thing that you would expect, you can prove in this kind of theory. So you have all these results from quantum toric geometry. But what I want you to remember is that above every quantum toric variety, there is a canonical complex non-scalar method. A canonical complex non-scalar above every quantum toric variety. That is the thing that is being Kronecker foliated by parts to produce the quantum toric variety. So this is the foliation that produces the quantum toric variety. So the quantum toric variety has kind of a canonical foliation on a scalar in a complex non-scalar. Well, then you have, now you can form modular space. And the modular space has the following quality, is as follows. The modular space has the property that behaves like this. It's a modular space, and then D, and then N. And just like the modular space for curves had a combinatorial invariant, typically it was M, G, N, where G was a combinatorial invariant, and N was a number of marked points. This modular space has a combinatorial invariant that is the poset, the combinatorial poset of the fan. So this is we should call it the genius of the toric invariant. This is a combinatorial invariant. Of course, from just this poset, you know you can compute the Betti numbers or the other characteristic. You just counting elements on this poset. So really, it's like the combinatorial invariant of the toric variety is poset of the, and N is the rank, is the number of marked points, is the number of irrationalities in the quantum lattice, is the rank of the group. So if you want to say, or the number of marked points in the fan. So remember, you can think of a fan, and the images of E1, E2, E3 by H bar, you can think of them as marked points. So indeed, this is like marked points that regularize the space. You have to have marked points to make this space a complex solvable. You are in this case. So there is an enormous analogy between the modular space of toric varieties. You have to include all the quantum toric varieties to form a modular space. Otherwise, this is my all question. could you form a nice modular space of Toric varieties? Well, now we can form a modular space of Toric varieties. And then you can write naively its topology. It's some set. It's a very complicated thing, because if you try to put this on a computer, you can understand it, because a little error on one of the points could create or destroy combinatorics. So it's very hard to put this on a computer because it's really unstable. But anyway, you get the topology of the modular space, and you can explore the modular space. It's a connected semi-divised subset. So we know the number of connected components. It's 1, and then you can start studying the topology of the simple scaling. But questions like Harrer stability, and all these questions are wide open for topologists. The study of the topology of this modular space. Nevertheless, just keep this modular space in your head for Hodge. And now, when you can quantify the modular space of producing universal families, and just like these things obtained by the compactification is obtained by the generation, here it's obtained by the generation of fans. You start degenerating the fan, and then as you degenerate, as this B becomes horizontal, a cone disappears. So you have this degeneration of fan, and then you do all these modular spaces, and then you get the compactification of the modular space of Toric variety. And you can even get the big modular space, gluing all these. And it was done by the big modular space, and the compactification in general was done by Boba in his PhD dissertation. So you get this big modular space, this nice compactification. Now you can start doing many things. But you could go in the following direction. And now this is work with Katzarkov, Lee, and Lobat, Meersseman, Adam J. And well, you may start to think about Hodge theory in this context, and you start doing your baby steps. And so I'm going to consider these n manifolds, and I'm going to consider the question of what structure do I have there about the Hodge numbers. I'm going to consider the question, what about the Hodge numbers of these manifolds n that are foliated here, and then maybe I can say something about the Hodge theory, whatever it is, of the quantum Toric varieties. So let's start by baby steps asking for the Hodge numbers of the manifolds n that live above this complex non-killer manifold that live above the quantum Toric varieties. And in what I'm going to say now, I said, you remember that I was going to take the gauge transform, and this was given the Lupercio. But I'm going to know this dynamical system in the lambdas of the gauge transform. And in what follows, I'm only going to consider R2. So two-dimensional fans. But remember, the manifolds can be of arbitrarily large dimension because of the Markovs, even though the fan is two-dimensional, because of the germ. So even though the manifold n, whenever a germ appears here, the manifold n is multiplied by the 1 plus S1. And acquired a complex structure. Then it covers the whole story. This complex structure covers the whole story. In fact, automorphisms of this manifold remember the foliation. So it's really the complex structure that is encoded in the quantum Toric variety. It's really the complex, and this is kind of a serious complex structure. If you move this complex structure, and then as you change the topology, the complex structure gets transformed into a complex structure, and we will see a little bit how this is happening. Okay. So I'm only taking this, and the Siegel condition for the dynamical system means that the origin is not in the walls. So it could be there, but not in the walls. It's the combinatorial condition that I need to have. Combinatorial geometric condition in the walls. So not in the walls. Okay, so I want to compute the local homology of these manifolds. I want to compute the local homology for all these various complex structures. It's a lot of them. So Well, of course, some combinatorics appears into the answer. So you try to use the Borel effect sequence you pay. To begin with, this could only help at the rational setting, and then you try to use it just for those complex structures, and maybe you want to vary the complex structure and see what happens to the box. But if you try to use the Borel effect sequence, the differential rapidly is inaccessible. You cannot do anything with that. So we wrote a new spectral sequence based on the particularities of our problem. And we compute this orthogonally with our spectral sequence, not with Borel's spectral sequence. And we got this number as important in our setting. This is the number of non-adjacent non-adjacent pairs of sides on the polygon. And remember, we're only in dimension 2 for the fact. So we get this SL is 2, SL is 5, SL is 9. Well, also 9 very much the case of an interval that is not a polygon. I also tell you what the answer is for the interval that is not a polygon. This is in dimension 1. The only answer in dimension 1, and then the ones in dimension 2. Full answer for that. Okay, this is the answer in dimension 2. The Hodge numbers are that thing. Okay. And SL appears there as a coefficient in the second product of 2 in this quadratic expression from the total numbers. So, well, it's a formula, but we would like to understand a little bit why and how you want to complete the structure. Well, this happens a lot already. Observe that that it only depends on the topology of N. It does not depend on anything else. I have all these truckload of complex structures on N, but it doesn't depend on the complex structure. And it's even more stable than that. Some of these complex structures don't even belong to the same deformation class. Nevertheless, they are the same. It only depends on the topology of N. So, well, that's the answer. But let's try to understand. I mean, this is just a really complicated problem. Can we understand something out of this problem? Okay, so a particular, well, let's take the interval. Let's go one dimension lower and not polygons, but just take the interval in dimension 1. And when we take the interval in dimension 1, we get the Hopf manifold and all its quadric manifolds of the topological form S3 crosses 1, this is H, crosses 1 crosses 1, crosses 1 crosses 1, crosses 1 crosses 1, this is N equals 3. And all these, we have all these beautiful mixed complex structures on these manifolds. We call them the quadric manifolds for obvious reasons. We call them the quadric manifolds. HM is what corresponds to the interval, and as many irrationalities in one dimensional quantum lattice as n additional irrationalities in the one dimensional quantum lattice. Algebraically independent one of the other. So they are algebraically independent one of the other. Well, then these are the Hodge diagonals of H1, H2, H3, and H4. Well, I know it's too small, but it's only H3. And you get this beautiful Hodge Pascal field. So every Hodge diagonal is a floor of this pyramid. And if you take this field window 2 by 2, and you add, and you see the first floor, and you add the 4 numbers in the window 2 by 2, you get the number exactly below the window. And you do it for all possible windows 2 by 2, and then you get the second floor of the Hodge Pascal pyramid. And then you do it again. And you do these 2 by 2 windows, and you get the third floor of the Hodge Pascal pyramid. So you get all these beautiful. Now you can predict the Hodge numbers of any one of these manifolds by these recursion of having these Hodge Pascal non-triangle field the dimensions. Well, what this means, of course, is this recursion formula. This is what it is. But the obvious thing is to take the generating function. I mean, the expression for the classical Pascal triangle It's better express yourself Q plus B to the n plus 1 Q plus B times Q plus B to the n. So that's the classical Pascal triangle. So what you do is you form the Hodge polynomial. Now, here a lot of things will of course, now we don't really have a theory of mixed Hodge structures or Hodge structures or anything like that. So even the notion of Hodge number for all these non-Kähler manifolds, you have various notions because of the Dini-Valrena behavior, partial behaviors of the Dini-Valrena. So you can do this for algebraic varieties, and then you expect nice properties, but you don't really expect nice properties, and they don't have nice properties for non-algebraic varieties. They don't have the user property that it doesn't have the user properties. But for algebraic varieties, you have that it has all these very nice properties, additive, family covering, multiplicative, Zariski-Doppler linear acceleration. The polynomial behaves very well, and gives you a lot of computation power about the numbers. This is a way to say that it's a homomorphism from K0 bar, from the, let's call it motivic ring of algebraic varieties of the complex numbers, to the ring of the polynomial ring into variables. This is what this is saying. In any case, this thing that this is the formula for the manifolds line about quantum toric varieties, and this formula can be rewritten like this. And this is the Hodge polynomial. This is using a little bit of the theory of hypergeometric functions 2 at 1, Gaussian theory of hypergeometric functions 2 at 1. You can reverse engineer this combinatorial number into the generating function. So you do this hypergeometric series and blah, 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 and then you get the slope. And this is the formula for the polynomial LM, where you start with one of these L's, and then you have M copies of the 1 versus 1. The smallest one is N associated to the polygon on L sides. N is the number of S1 versus 1s, or the manifolds with quantum lattice, and then in the number of sides in the polygon. And that's the polynomial. Notice that now recursion in solvers is multiplied by a unit curve. So this is, for example, this is for the one-dimensional segment example of the quasi-Hopf manifolds. This is the formula for the quasi-Hopf manifold. The next quasi-Hopf manifold, you also obtain the polynomial by multiplying the polynomial by that of an elliptic curve. So it's a rather drastic simplification with respect to all these complex structures. And well, the only important one is EL minus 2, of course. All the other ones you generate multiplied by elliptic curves in terms of the polynomial. And what this is saying is that there seems to be this kind of polynomial that allows you to perform a motivic log transform at the level of K0 bar or K0 or polynomial. So there seems to be this polynomial is the term for the log transform in this case, and this particular log transform. So we have this that we call the first logarithmic transform difference polynomial. And I put in quotation marks this difference P1 plus C minus H. Because while K0 bar is a very interesting ring, K0 complex manifolds is nothing. It's so flexible, contains no information. So this thing doesn't exist in any place. So you're puzzled, because this has very nice motivic behavior. This is K0 bar. But in the traditional case, the theory of the lead implies this famous conclusion that this is a universal morphism of rings. But to prove this, you need this theory of mixed Hodge structures of the lead, Hodge theory. So, but now we don't have anything like that yet. The actual computations are behaving as if we did. when we do the computation, behaves, and then we can take the long transform as a polynomial. So this is all possible, isn't it? It's very possible. You can do all these sorts of calculations, and here there is no quotation marks. But if you keep doing this kind of calculation, at some point you have to write quotation marks, like here, P1 cross P1 cross C cross E minus H cross A. This thing doesn't really. Nevertheless, the final conclusion is true. If you compute the polynomials using the formula, now the final conclusion is true. So even though there is no case zero complex manifolds to work with, if you act as if there was, you get all these nice calculations, and then you solve this problem that is a complicated combinatorial problem. So if you can even do these heuristics to go back, like you wanted to go from d-dimensional funds to d-1-dimensional funds. You even can do this kind of heuristic tricks to change the dimension of the fund. And then you know that there is this theorem of Hodge and Schreiber, that the only universal linear relation between Hodge numbers or smooth proper values of an arbitrary thing are the ones given by Z1. Notice that in our terms, all the one for the Hodge, you have no other relations. You have only the one given by the Z1 T. Nevertheless, for K0 bar, you have three polynomials that generate all your Hodge values: P1, P2, and E. And this is not what we're seeing. In our case, the Hodge is there and it's generating in our computations. We need H to generate all the Hodge values of all the varieties. Nevertheless, in characteristic P, using an example of Jean-Pierre Serre, double proves that you need one more thing that behaves exactly like the Hodge metric in characteristic P. And this is exactly what we're seeing. So what's going on? Now we're super puzzled. What we're seeing is the behavior of characteristic P for the complex numbers in a ring that doesn't even exist, because it's said. We're seeing all these behaviors, so we are very, very puzzled. Well, the solution to the puzzle is what I mean. And all the ends, we can prove that all the ends are generalized complex numbers. This is very interesting, but this allows us to generate all these Hodge diagrams with this H thing, just to show that all our Hodge diagrams are being generated like in characteristic P. This generalized one transform is what allows us to do that thing. Well, let me just give you the punchline. While there is no K0 complex manifolds, there is K0, let me call it, definable manifolds using all minimal structures. So the puzzle is solved because we can prove that for the various definitions of HPQ and for various all minimal structures, for example, R and X, where our manifolds live, there is a K0 definable and motivic ring of definable complex manifolds. All of them land there. Then these calculations were happening in the motivic ring of, and this theorem of characteristic P is true in the O minimal world. So the theorem in characteristic P, you have it back in the O minimal world, and you need P1, E, P2, and the Hodge surface. And that's all I want to tell you today. Thank you very much.
So, any questions?
So do I understand correctly that you're considering all of these algebraic varieties, these projected algebraic varieties, basically principal abelian bundles? Is that the class? Does that capture the class of manifolds? The principal bundles with group the building plan.
Almost. It captures a variance instead of these complex structures. This is the rational policy we will show. But of course, you need the ones that are about chemical conditions and the corresponding. You have a new complex structure.
So does that mean
So interpolating between different complex structures in the L space, in the total space of the interpolating between these complex structures, there is you need to move in through conditions.
does that mean that it's a principal bundle, but not for an abelian rendering or a complex compact forest?
Yeah, sometimes it's not variety, but yeah, it's not a complex source even. Sometimes it opens up and becomes stronger condition on the same topology, on the same CP.
So what is N? What kind of math? What kind of complex manifold is N?
If, for example, take this manifold here. It's what you said, but you can give it more complex structure than the one you described. Even more. And typically, you are not going to know this is what we prove to. Well, sorry, not the whole time are going to know. But the projection is that quantum phenomena in the general category might know this. Because there may be some zero devices that are looking at motility. So this is extremely subtle how some new complex structures come about. And the way to see them. Well, this has a reflection in the extremely beautiful work of Leonardo. They are considering a non-abelian version of this, where they take the seventh sphere, and they are seeing the various differential structures of the seventh sphere by this kind of behavior. And we can see it motility. It's a non-abelian version. And so zero divisors in these all minimal typically are expected to see Kerber moves.
However, if I understand correctly, I must also get a drawing from this association.
That's right, in some cases, but for a non-commutative space.
Yeah. Is here what kind of special remaining methods to use total spatial division methods?
Well, no, this is a question that we have tried to jumpstart at various occasions, but we haven't had the momentum to explore. But we should talk more about that. It's very interesting. We know a little.